Hello guys, Kesh this side. During one of my meetings recently, a very important thing came up about the floating point precision which is available on our devices. So I was just curious that how much precision we can utilize in our calculations without having errors. So I went on and found out a way to test out with how much precision we can have a compare statement run the comparison that we want to carry out. So for example, if I have a number with the precision of 10 decimal places, will I be able to make proper comparisons? So for example, I want to test out if 2.656565 is equal to 2.65656565. Will my computer be able to handle such calculations? Suppose if I increase my decimal places for up to 64 bits, for up to 64 decimal places after the decimal operator, will it be able to handle such kind of comparisons? So I made a small program to find it out. I'll open this program right in front of you. So this file, in this file, basically it took me a long time to get to this place. So here I am using 32 decimal places after the decimal. If we count the number of zeros here, it will come out to be 31, and 32nd is the this one here. So I ran a loop. I increment my loop by this value, the precision value, while my iterator starts from the value 0, and then I compare the value with my iterator. So if my iterator is able to add this value one by one, that means increment all these 31 zeros and 1 to my 0, and is able to properly compare the two values, that means iterator equal to value to check if it matches out, it will says that the precision value works. That means we have 32-bit of precision available. So I ran this program, and suppose if it doesn't work, it will simply say that the precision value did not work, failed precision value with this mantissa. So one by one, I started from bottom, starting from 15 decimal places. I came up to 32. After 32, it is failing. It doesn't go beyond 32. It is not able to compare with precision. It fails the comparison itself. The CMP instruction itself fails. So I'll run this program in front of you and show the output. So I will write GCC float underscore precision let's see, hyphen o. I'll do run underscore body. Okay. Then I'll run underscore body, and I'll save it to show underscore audience .json. Then I'll open this and show you the output. So you see, the precision value works. It is able to compare the value which was needed to be checked. So it iterated by incrementing 1 in the end, and finally it was able to compare the 9 successfully. Now till 32 places of decimal it worked properly, but when I increase this, then it fails. And for that I'll show you another program. Let's go to C. I'll run RD. First let's first see what I have written inside the code, so that you are abreast with the functioning. So I started here with 39 decimal places, and it checks if suppose if it does not find it is not able to compare, and the iterator value goes beyond 10 iterations, because after 10 iterations the incrementer will go to 10 instead of 9. So if it is not able to do it within 10 iterations, then it enters this part of the loop, and the mantissa is decremented from 39. It goes to 38 decimal places. The precision value is multiplied by 10, so 10 gets removed from the precision value. Similarly, 10 gets removed from the value which is needed to be checked. Iterator is sent back to 0, and the counter, which is counting the number of iterations, is also sent back to 0. And similarly, when the precision is equal to 1, eventually when it goes on multiplying and reaches 1, then the program breaks, and we are out of the system in this case. So I'll run this program, and we'll see that this program beautifully fails. I mean, the entire FPU implementation of the machine basically crumbles. So usually some software controls are used so that our program doesn't land up in such a situation. So good programmers, experienced programmers, utilize this concept and machinery in very efficient fashion to get us correct values as output. But this is what we should know as a concept while operating on these machines. Let's run this program and see what happens if I run this program. So I'll do GCC, compile this program, -o, run _Audi _2, then run _Audi _2, and send it to show _audience _2 .json. Let's see the output. Nano. Show _audience _2.json. So you see it says failed at precision value this much. I had given 41 zeros after decimal point, so that is why it is printing 2 zeros extra after the 39th value. Similarly, if we scroll down, it simply says it failed, then failed with 37. It keeps on failing because the error keeps on getting added to the base value. See, in the comparison after 35, I am getting this 3 in the end, and the error margin and the error keeps on increasing with each iteration. See, earlier the error was getting incremented by a value of 3, then it increased to 4, then it increased to 30 after 34. From 30 it is going 60, so the error margin is increasing with every iteration. So eventually this error margin becomes so big. I mean, these are very few iterations which I am doing in this program. I mean, I am doing roughly less than 200 iterations in this program, but for larger data sets, in fact very large data sets with very high precision calculations, this error computes to very large values eventually, resulting in a very wrong output. So operating the FPU of the device carefully and getting the correct value out of the system is very important, and this concept should be known by every good programmer here. So see, 32 at 32 Mantissa we get the correct value from the laptop, but because the error margins have already increased to such high values in our previous steps, it is not able to verify the output, and the comparison fails. 32, 31, it will fail till the end. It will never match because the error margin keeps on getting increased. See, the error is increasing, 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 increasing. So yes, so you see, I mean, because the floating point unit implemented in every machine follows a IEEE standard, and the standard itself is not perfect in implementing the numerical calculations that require very high precision. So it is up to the person who is making the program, who is implementing the algorithms, to get the correct value out from the equations that he has implemented. So it is possible for many problems that are being solved using these algorithms, they land up with wrong values without the person knowing about it. Usually with programming languages, other higher level programming languages, we don't get to see these nuances. They are never presented in front of us. We simply get whether our output is correct or our output is wrong, and we simply keep on banging our heads for wrong reasons. Uh, so yeah, that's all. Uh, Thank you for watching this video.